First of all, I'd like to thank Daria Pushinskaya for asking me if I wanted to give a talk here in this seminar, and also I would like to ask the organizers of the seminar to give me that opportunity. So what I will talk about today is Morrey's inequality, which is a classical inequality in Sobolev spaces, and this is based on joint work with Ryan Hine, who is at the University of Pennsylvania in Philadelphia. So let me just start very frankly with the equality I have in mind. So this is the version of Morrey's inequality I intend to talk about. So we have a bounded and open domain, omega, and then you have this inequality that I will explain what this C1 over 1 minus n over p norm is, but there's a norm of continuous function which is bounded by a constant times the LP norm of the gradient. And I'm not used yet to giving online talks, so let's see if I can write here too. So here when I have written u and then c and some exponent, which here happens to be 1 minus n over p, I simply mean that we have two terms here, the L infinity norm plus a semi-norm, where the semi-norm is simply this Hölder quotient. So you take the supremum over x and y, and you have u of x minus u of y divided by x minus y to the alpha. So I hope that you can read this. So the term here contains two terms, the infinity norm and the semi-norm C alpha.
Don't forget the modulus.
Oh, yes, sorry. Thank you for the reminder.
Without modulus, this is the same.
Yeah, okay. So I'm happy that already there are some questions and comments, and I encourage you to interrupt me whenever you want to say something. So if you just throw away the second term here, in particular, this inequality here implies this inequality. And the second inequality here that's in a box, this is the one I will be focusing on today. And so if you look for the smallest possible constant in this inequality, you can of course formulate it as that this is 1 over lambda p, where lambda p is the inf of this Rayleigh-type quotient. And here, of course, I was a little bit sloppy because on the first slide, I was looking at functions that are smooth with compactly supported in omega. Here I have written just the Sobolev space W1P 0, but which is just the closure of these functions with respect to this norm here in W1P. So we're talking about the same thing here. So you can, of course, think of this as some sort of limiting case of some maybe more well-known inequalities. So they have many names, but you have Poincaré's inequality, which is just something of this form. And of course, you could put different LP norms here. You could have LQ norm here and LP norm here, given of course that there is an embedding into that LQ space. So you can look at this as a limiting quotient where you have an LQ norm here instead of the L infinite norm, and you send this exponent to infinity. And of course, there are some connections between these problems when you have finite exponents and when you don't have finite exponents. So let's just see in some basic examples, what can we say about this inequality and the extremals? So what about the 1D case? So suppose you consider the domain, which is just the interval from -1 to +1, and then the inequality, in fact, reduces to this. And how can we see that? Well, you could simply, if you assume that the function, let's say, is positive and attains its maximum, it's not hard to believe that the maximum for an extremal should be at the midpoint. So then let's try to see what happens if we just write that u of x. Well, this is just the integral over of the derivative, let's say of some point y dy. And of course, if we take absolute values here, and use Hölder's inequality, we can estimate this in terms of, so you get an LP norm on the interval -1 to x, and then you'd get basically just the power of the length of the interval to the power of q, if q is the dual here, exponent of q. And then if you assume then and think that the maximum value of u is attained at 0, which is the midpoint, you get that u of 0 is just bounded by, then the term with x plus 1 just becomes 1. So it's just bounded by the LP norm from -1 to 0. And then maybe it's not hard to believe that you would have some symmetry on this set, which is very symmetric. So this will just be, in that case, if we have symmetry, this will be 1/2 of u prime over the full interval. So at least for symmetric functions that attains the maximum at 0, you will have this inequality. And then you can say, okay, what happens if you have equality here? Well, we'll use Hölder's inequality for the integral. So basically, if we have equality, then the derivative must be constant. U prime must be constant. And then this forces the function to be of this form here, up to a multiplication with a constant. So what I was saying here is that equality would imply that u prime is constant. So in the one-dimensional case, it's not so hard to dig out the details here and to see that the extremals or the optimal function attaining the optimal constant here is of this form. Okay, so this is maybe the simplest possible example you can think of. And let me also mention another well-known result, which in fact is something I will not nearly touch, but it's quite important for what I will say later. In any case, it's the case when omega is just the full space. Then, of course, if you think of the scaling of the right-hand side and the left-hand side of this equation, you cannot have a constant which is completely independent of the function u. So the proper inequality in this case takes also into account the size of the support of u. And this inequality here was treated by Talenti. And he proved that optimal functions here in this inequality has to be of this form here. So basically in if you're in the unit ball, so if omega is just the unit ball, then extremals will just be 1 minus x to this power, p minus n over p minus 1 in the ball and 0 outside. So typically the profile is something that I try to draw here, but there's some sort of cusp here at the midpoint, since this exponent here is less than 1. So this is quite important. Okay, so for some reason this is not working. Yes, so these are the basic cases I'd like to just mention here. And it turns out that this example by these functions of Talenti are quite central. It turns out that in a general set, there will be a specific point, which will be the maximum point of these extremals, where the function behaves exactly like these functions. So this is sort of an important function to have in mind for the rest of the talk, which are these functions that I tried to draw here. You can probably draw them better than me. And so just a comment before I try to explain a little bit what's known about these other inequalities, like Poincare inequality, is that sort of the basic idea I would like you, if you want to remember something from this talk, this is the basic idea of one variable calculus that I would like you to recall, so that if you have a convex function and if you have, then it's well known that this has if it's strictly convex, then this has a unique minimum. So what is the idea? Well, the idea is that if you have two minimum points, well, then you just apply the convexity, and you can see that f evaluated at u plus v over 2 is less than the mean of f of u plus f of v over 2. And then this, of course, also has to be equal to the minimum value, because it's the average of these two. And then if the function is strictly convex, then you have equality here in this convexity inequality, and that forces u and v to be the same. So this, of course, everyone has seen before, but this is more or less the basic idea that I will use, and also I will explain for some other problems that people have been using in order to prove some uniqueness property of minimizers of these problems. So this is something that it's good to have in mind. So something I forgot to mention, if I just go back here, and that will be common for all problems I will talk about today, is that if you look at this quotient here, which is the quotient we're looking to minimize, it's invariant under multiplication with a constant. So whenever I'm talking about uniqueness, I'm talking about uniqueness up to multiplication with constant. So you can never have pure uniqueness here, but it's uniqueness up to multiplication with the constant. Okay, so let's go back to this problem when we have finite exponent. So let's instead, to start, look at this problem. So it's actually the Poincare inequality, right, in W1P with zero boundary data. So we're looking to minimize this quotient, And in this case, it's pretty straightforward to compute the Euler-Lagrange equation for extremals. So you take the first variation of this quotient and you simply compute. Both the enumerator and the denominator are differentiable, so you can compute the first variation. And it simply becomes this equation here. And even though I think many people in the audience are very familiar with the P-Laplacian, let me just write it out here to be on the safe side. So the P-Laplacian here is just the divergence of the gradient to the P minus 2 gradient of U, and arises as the first variation of, if you just look at the term with the gradient to the P. So this is sort of a nonlinear counterpart to the Dirichlet principle for harmonic functions, that harmonic functions minimizes the functional consisting of the integral of the gradient squared. So if you instead look at the integral of the gradient to the P and look for minimizers of that, you simply get functions satisfying that this operator here, P Laplacian, is equal to 0. So then it's not so hard to believe that if you have this involving this, you will get something where this operator pops out, and then you will get something coming out when taking derivative of this. Okay, so what can you say about this problem here? Well, in fact, it turns out that for any connected bounded and open set omega, there is only one minimizer here of this problem up to multiplication. So this is a result proved by Lindgren in full generality in 1990. And the idea is very, very simple. And it all goes back to basically the convexity inequality I wrote out for a 1D function. So it's important to note what I said here, that if you look for minimizers of this, you might as well, since the quotient here is invariant on the multiplication with constant, you might as well look for minimizing this quotient over functions which has LP norm equal to 1. So you might as well assume only look for functions U with the LP norm equal to 1, since you can always multiply with a constant so that you obtain this. Okay, so how can you go about to prove that minimizers are unique up to multiplication with a constant here? So basically the idea that you have here, and also the idea that I will explain later for the Morrey problem, is that you assume that you have two minimizers, and then you want to produce a third minimizer of that. So this is exactly what I did with this convex function f, right? I assumed that they had two functions, 2 points where this attains a minimum, and then due to the convexity, I produced another point. And then I used the strict convexity to say that if we have equality here, the points must be the same. So in fact, this is what you can do here. So I will just present the proof in the case p equals to 2, because the idea is exactly the same for general p. And this is not the original proof. The proof I'm presenting here is in a paper by Ballone and Cavol from 2002. But the original proof is not so far from this either. So that is, we assume that we have two extremals where the L2 norm is normalized, so it's 1. And then we want to find another competitor. So we want to find another function which also has L2 norm equal to 1. Okay, so what do we do? Well, one way is to construct this function. You take the average of the squares and you take the square root of that. Then obviously the L2 norm of this function will be 1. So then it just boils down to, can we say something about the L2 norm of the gradient of this function? If it turns out to be less than or equal to the average of the L2 norms squared of u and v, well, then we're in a good position maybe to apply some convexity inequality. So what happens? Well, if you compute the gradient of w and you make some rearrangement, you can see that in fact you have this inequality here. And what do we have here? Well, we have this coefficient here in terms of gradient u in front of gradient u over u, this coefficient here in front of gradient v over v. So if you sum this and this up, this sums up to 1. So here we can use the convexity of the function that maps x to x squared for vectors then. So if you use convexity of this function here, the square, we can bound this by just the gradient u squared and gradient v squared. Okay, but then if u and v are extremals or minimizers, then this new function is also a minimizer. So we have constructed a new minimizer in that case. Okay, but then since this was the minimum, we have equality all the way. So then we know that the function that maps x to x squared, this is a strictly convex function. So strict convexity is important here. So this means, in fact, that these functions must be the same. Gradient u over u, gradient v over v, or gradient of log u, or gradient of log v. So if these are the same, it is not hard to argue, since they have the same boundary values, that they must be the same. So basically, this is the proof. You can do the same thing for general p instead of exponent 2. You just compute the gradient of this function, you exploit some convexity inequality for the square function, and then you say when you have equality, these guys must be the same that you had in this function. Okay, so this looks like a fairly easy proof when this was for the case when we have LP and LP, where the proof was for L2. So this was for this problem. So you have the same exponent here. So then you might ask, what happens if you, instead of the P here, change it to a Q? Well, instead of the P here, change it to a Q. Okay, so then the problem becomes just this, but we take an exponent here in order to make the problem still invariant under multiplication with constants. And then, of course, you need some restriction on Q in order to have the embedding. So you can compute also the Euler-Lagrange equation straightforward from this. It looks a little bit more nasty, but you have the P Laplacian still, and then there is a nonlinear factor here in front of u to the q minus 1. And it turns out that the problem here changes dramatically at the threshold p equals to q. So what's known is that when q is less than or equal to p, then you have this uniqueness property up to multiplication in connected domains. And in general, if you have p equals to 2, and for all the q's you can think of, except for the critical one, you also have uniqueness in convex sets in the plane, which is kind of an interesting article by Lane from '94, which sort of does a linearization argument to prove this. And also there's some other specific symmetry assumptions that can be used, still in the case p equal to 2, to prove that you have this uniqueness in the plane by Dancer and Damaschelli and Grossi and Pacella. And it's also true in general if omega is a ball, you can actually work with radial functions. But something happens when Q goes above P. And in fact, this uniqueness property is destroyed. So in fact, one of the organizers studied this problem in a paper from 2000, where it constructs a counterexample to this uniqueness in an annulus. So if you have just an annulus, and I think then when the quotient of the radii of the analyzed is very small, then you no longer have uniqueness for this problem. And there's also a quite recent nice counterexample in even a simply connected set by Lorenzo Brasco and Giovanni Francina from 2019 in an overview of similar problems. So let me just write down here. So what do we have? So one counterexample is when omega is, what should be that they are more close, I think. So they should be two balls, let's say BR1 minus BR2. Or the other counterexample, which is simply connected, is when you have two squares and you sort of connect them. And where this part here is very thin. So the first, of course, is not simply connected. The second example is simply connected, which shows that it's not only topology of the underlying set which affects whether you have this uniqueness or not. It's in fact the geometry of this set. And this is even a set. The second example here is even a set which is star-shaped with respect to a neighborhood of the origin here, if this is the origin. So it's clear that this is a geometric, might be some geometric property that affects this. Okay, so this sort of was the sum up of some results for this general problem when you have the LP norm of the gradient and LQ norm of the function. So let's go back then to the problem that I intend to talk about, so which is again that you have the LP norm of the gradient and then the L infinity norm of U. So what was the first thing I presented for the other problems? Well, that was the Euler-Lagrange equation. And it turns out it's a little bit more tricky to find the Euler-Lagrange equation. So this part here poses no problem. You take the first variation of that, you end up with the P Laplacian again. And here, of course, you have the L infinity norm, which is in some sense less nice than the LQ norm of the LP norm because it's not differentiable. But it turns out with a little bit of work, you can actually extract what the proper Euler-Lagrange equation is. And it's a little bit interesting. So as you might expect with L infinity norm, if you have the max or mean, there is a measure coming out when you take the first variation of this. And this is exactly what happens. So this was first derived by Ercole and Pereira in a paper from 2016, I would like to mention also. So the equation reads that the P Laplacian or minus the P Laplacian is equal to, well, lambda P is just the optimal value here. And then you have U to the power of P minus 1 with the sign times the Dirac measure at the point x0. And what's important here, and it's kind of special that you get this information from the Euler-Lagrange equation, is that x0 here is the unique point where the absolute value, the modulus of U, is maximized. So already from the Euler-Lagrange equation, you can read off that there's a unique point where U is maximized. So what does that tell us? Well, it tells us that you have your omega here, and there's a point here, x0, which is the max point. And outside of this point, the function is in fact p-harmonic. And of course, it's always 0 on the boundary. So it's p harmonic in the puncture domain. In fact, there's only one point where something happens to the operator. So this is the type of functions that comes in when you want to study the extremals of this problem. Okay, so let's look at some other first considerations that you can do with this. Well, first of all, there's a one-to-one correspondence with this Euler-Lagrange equation and the minimization problem, which is not so hard to see. If you multiply this equation with u and you integrate on both sides, integrate by parts on one side, you get exactly that any solution of this is a minimizer. Okay, what more can you say? Well, if you look in this drawing here, the function is 0 on the boundary, and the modulus of u attains its max at the point here. And at all the other points, the function is p harmonic, so you have the maximum or the minimum principle for the p Laplacian. So this means that u will be between 0 and whatever value it has at the point x0. So depending on the sign, it will be either strictly positive or strictly negative. Okay, so then if we just multiply with -1, if the function happens to be negative, we may always assume that u is strictly positive in omega. And of course, like for all the other problems, we can rescale. So we may assume that the maximum value of u in this case is 1. Okay. So then we have a function which is 0 on the boundary, 1 at some specific point, and p harmonic at all the other points. So then the normalized equation is exactly what I said. You just have a Dirac measure times the optimal constant here, lambda p, and the function is 1 at this point. Okay, so then this brings us natural to consider so-called potential functions. And the potential function is just that given a point x0 inside omega, you can of course solve the equation where you put the function to be 1 at this midpoint and 0 on the boundary. So this is what I just call potential functions. Okay, so then you are given a point and you solve the equation with boundary data 1 at x0 and 0 on the boundary and p harmonic elsewhere. Okay, but then you might have objections here saying that, well, how can you prescribe boundary data at one point if, harmonic functions? Can you do that? Well, not really, right? But the thing is here that we have all the time, which I maybe not emphasized, assume that p is larger than n. So when p is larger than n, in fact, for this operator, all boundary points are so-called regular points. You can always prescribe boundary data when p is larger than n, which is not true if you go below. So there's actually not any problem with prescribing this value here. Okay, so we're interested in uniqueness. So basically, when we have set the sign here that u is positive, and we have assumed that the L infinity norm is 1, we have normalized. So then, in fact, the uniqueness we're talking about here is like really saying that there is a unique function which is positive, that has max 1, and that solves this problem. But then this question is really about saying that there is only one choice of x0 that gives this potential function the proper Rayleigh quotient. So note here that for any x0 we can solve this problem, but it's not clear that any potential function solves this problem. So the lambda that would pop out here if you compute the equation for this will depend on where you put your point x0. So really, the question is, if you look at these potential functions, which are just, you take u to be 0 on the boundary, and 1 here, and p harmonic here. So the question is just, is there a unique x0 in omega such that, well, either p Laplacian is equal to this lambda p times the Dirac at x0, or if you want, that the energy, which is the LP norm of the gradient, is exactly the optimal constant lambda p. So this is the question that we ask ourselves. If you move around this point x0, is there only one choice that gives you this? Okay, so the equation we have is this. So what can you draw? What kind of conclusions can you draw directly from this? Well, you can draw some conclusions about when you don't have uniqueness. Okay, so if you have an annulus, what happens? Well, you have one ball and you take another ball, and this is supposed to be spherically symmetric. Then the equation says that there's a unique point where u attains its max. So there's a unique point x0 here, where u of x0 is the max. Okay, but then it's p harmonic everywhere else. And of course, if this is an annulus, you can always rotate it and also get another solution. So it's clear that in an annulus, the solutions are not, the minimizer is not unique. It's unique up to rotation, but it's not unique up to multiplication with a constant. And this comes directly from the fact that this maximum point is unique from the equation. Okay, so this was a kind of a simple observation. And another interesting observation is the following, which is a little bit more tricky, but if you have a set which looks a little bit like the counter example I drew, so it's supposed to be symmetric, and it's this part here is supposed to be very thin. Then it turns out that you can, by a limiting argument, prove that in such a set you cannot have uniqueness, because if you have uniqueness in such a set, the maximum must be attained in the center. Otherwise, you can reflect and get another solution. But then if you pass to the limit and let this part in the middle shrink to a point, then you should get the minimizer of the limiting problem. But this is not possible, because if you have the maximum here and the distance decreases to 0, then the energy will blow up if you go from 0 to 1 in smaller and smaller in a smaller and smaller set. So in fact, you have two examples where you don't have uniqueness. So then we started to ask ourselves, when can you expect uniqueness of this problem? And for many of these problems, convexity of the domain seems to be a natural assumption. So we started to work under the assumption that the underlying domain is convex. And so it's kind of technical, but let me just try to point out what are the main points, the main reasons we can do this for convex domains. So we were able to do it for convex domains, and also using maybe more standard methods, symmetrization methods, you can also prove that there's a unique minimizer in Steiner symmetric domains. So I don't know if I have time to discuss the second theorem, but this is also something you can do. But let's now focus on the convex domain and see what we can say. So there are three main ingredients. So remember that any extremal I said to be a potential function, and potential functions with those I just said that you fix a point where the function is 1 and then it's 0 on the boundary, and you solve the P Laplacian outside this point, the P Laplace equation outside this point. And And these functions have been treated by Lewis in a classical paper. So these results are very important for us. And then there's a paper I will mention in a few minutes about p-harmonic functions in punctured domains. So recall here that we have a solution to the p-harmonic equation outside omega where you take away x0. And it turns out that this behavior looks exactly like the behavior of these functions of talented that I presented in the beginning. And then there's the third thing I would like to mention is the Minkowski combination of functions. I will come to that in a minute, which is a way of constructing a new function out of two functions, where you can sort of, by adding up the level sets of these two functions. So what is known here for these potential functions? So first of all, those of you that have studied the P-Laplacian, which I know that there are several people here that know much more about the P-Laplacian than I do, but you know that the P-Laplacian, well, is the divergence of something containing the gradient to a power. So at least when P is larger than 2, this thing here vanishes when the gradient vanishes. So you might, there are additional difficulties when the gradient vanishes, but it turns out that in convex domains, when you solve this problem, so these potential functions, the gradient never vanishes. So you sort of get rid of that problem. And this and some other results are proved by Lewis in a classical paper. And one important property is that the function, any solution of this problem is quasi-concave, so that the level sets are, super level sets are convex sets. And in fact, the function is real analytic outside the point x0. So you can do all kinds of computations with these functions. So this is very important. And the second result, more in detail, is that
Eric,
yes.
Excuse me. This fact is true in convex or strictly convex domains, the Lewis result?
No, I think they're true in convex.
Okay.
The bounded domain, convex bounded domain. And so the second result I mentioned here is that if you look at the behavior of these solution potential functions near the point x0, they behave exactly like these Talenti functions, with the constant here that you can determine in terms of this energy, which is just the integral of the gradient u to the p. And you can also determine the asymptotic behavior of the gradient near this. So the gradient has a singularity at this point x0. But even more interesting is that if you have a potential function and it behaves like this, but where this lambda is the correct lambda for being a minimizer, then in fact, this is a minimizer. So in some sense, you can say that having the correct asymptotic behavior is equivalent to being an extremal for potential functions. Okay. And
who is the author of this observation? It is, I think, the key idea here.
So this is in a paper by Kishanasamy and Veron from 86.
Okay.
Yeah. I think, well, actually they proved one direction, and then we sort of worked out a little bit stronger implication in the other sense, but I mean, the results are theirs.
I think they were not interested in the minimizer.
No, right. They were not looking at this problem.
Yes. But in your problem, it is the key point.
Right. Right.
That you can look only to the neighborhood of the extremal point.
Right, exactly. Yeah, this is this is the key point. Okay, and maybe the most confusing part of this talk, or maybe there are other confusing parts, but is this third thing I would like to mention is the Minkowski combination of two functions. So if you have two extremals, U1 and U2, and you know that they have convex superlevel sets. So then there's a way of defining another function, which is called the Minkowski combination, which is, the formula is a little bit confusing. You have to think for a while and to see what happens. But there are some important properties of this, is that you construct a new function. So if the function U1 and U2 has their maximum value at x1 and x2, then this new function will have its maximum value at the midpoint of this, and it still will be 0 on the boundary. So it will be a competitor for this Rayleigh quotient. And if you don't like this formula, you can also think of what this is doing is that for this new function, the level set of this is just the Minkowski sum of the level sets of U1 and U2. So let me try to maybe draw some explanatory picture, which could be that you have, suppose that, this is your U1 and this is your U2. Then when you construct this new function, it may look like something like this. So this is the U. And here will be then the max point of x1, the max point of x2, and somewhere here will be the maximum point of U. And also a very schematic picture is that suppose that these are spherically symmetric functions, so that, this is the graph of a function, so that you have a level set of U1 maybe looking like this, and then the same level set of U2 looking like this. Then U will be somehow have the Minkowski sum of the level sets with an average. So the level set of U will maybe be, maybe that was not too pretty, but something like that. So the whole point is here, of course, that you take 2 point x1 and x2, and you take two extremals. Suppose that there are two extremals corresponding to having the max at x1 and x2. And then we construct this new function u, which has the max here at x1 plus x2 over 2. And then the point is, of course, to try to prove that this new function will be an extremal and somehow conclude that this forces all these functions to be the same. Okay, so hopefully this explained a little bit what the geometry sort of idea is behind this. But there's one more point to this Minkowski equation, which is crucial. So there's a series of nice papers by some Italians, Colasanti, Longinetti, and Salani in 2003, 2007. There are also other related papers, where in fact they prove a differential inequality for this Minkowski sum. So they prove that, if you ignore the power of the gradient here, they prove that you can estimate the P Laplacian of this new function in terms of the sum of the P Laplacian of U1 and the P Laplacian of U2. In particular, if these are solutions, which they are in our case, outside this point x1 and x2, then this is 0, this is 0. So this gives you that, in fact, this is a sub-solution to the equation. And more importantly, you have something that corresponds to this strict convexity, which is that if you happen to have equality here instead, then the level set of U1 and U2 will be the same. And in fact, in this case, it will force them to be the same function. So these are sort of the three building blocks: the properties of potential functions, this asymptotic behavior near the singular point x0, and this Minkowski combination and this differential inequality. So I will not go into the details on how to prove these three things. I will just now try to explain, so how do you use it? Okay, so what is the idea? Well, the idea is the same as before. You take 2 points and 2 minimizers. So that corresponds to these points. So U1 has it max at x1, U2 has it max at x2. And then you take this Minkowski combination, and then as we saw, or at least I said, this new function is 1 at the midpoint and 0 on the boundary. So it's a competitor for the Rayleigh quotient. And then by the previous inequality, this differential inequality, it's also subharmonic. So the aim now is, of course, to prove that it is a solution, that you have equality here, and then use this differential inequality in the case of equality to say that then U1 and U2 must be the same. So the main idea is basically to use the definition of this Minkowski combination. So in fact, U, if you go back to the definition of U, which was this Minkowski combination, is the minimum of these guys, where Z is just the midpoint. So it's the supremum of this minimum. So at least it's larger than or equal to this. And in fact, this is exactly what I said. So U is larger than this minimum, where X is the midpoint of Y and Z. And this forces a growth from below on U of X. And since U1 and U2, we already know that these are extremals, so we know that they have this exact behavior near their maximum points. So in fact, U inherits this behavior. And this forces U to be an extremal as well. But of course, you have to analyze this inequality and see that you get exactly this behavior. But this is the main idea, that U inherits this behavior from U1 and U2. And also I'm cheating a little bit here because we don't know that U is a potential function. We only know that it's a sub-solution. But in fact, if you look at how you argue for this, you can prove the same property for sub-solutions, not only for potentials. So this, in fact, this asymptotic behavior and this characterization of sub-solutions or potentials with this exact behavior near their singular point forces U to be an extremal. Okay, but then we're just at the situation where you have equality in this differential inequality, and this forces U1 and U2 to have the same super level sets, and they must be the same. It is not so hard to see. So again, if you just look back a little bit, what have we done? Well, it's the same old idea again. You have 2 extremals and you construct another one, and you try to get equality in some inequality and somehow use some strictness of this inequality to say that, in fact, if you have equality, then the functions must be the same. So it all goes back to sort of similar idea. The main issue here was, how do you construct a new competitor? Because the L infinity norm is, it's not so easy to work with. But it turns out that this tool of Minkowski combination really did the trick. Okay, so I think I will skip to talk about the other theorem with symmetry. And I will just go to the last slide with some, possible interesting questions related to this. So in my first slide, I wrote out sort of the true Morrey inequality, which contains the L infinity norm and the semi-norm. So we threw away the semi-norm. So maybe, in fact, the most interesting inequality could be instead if you look at the inequality with the semi-norm. This is something I would like to think about, but for when omega is the whole space, there's a series of recent papers, very nice results by Ryan Hind and Frank Seufert, where they actually characterize extremals and prove some symmetry properties of this. But for bounded domains, I have no idea what to do. And another question is that, how can we characterize these sets where you have uniqueness of extremals? Star-shapedness is not enough, but convexity is not necessary. So what can we say? And also, of course, this uniqueness for when you go from LP to LQ, when Q is larger than P, in convex domains, for instance, is not known. So these are some questions that one might be interested in. But I think I'll stop there, and thank you for listening. And here's a list of some references.
Great, thank you. Questions, please, or comments? Okay. I have the first question is, I think, just in the slides which you skipped. Why is your theorem 2 only two-dimensional? What prevents this result in 3D, for example?
Yeah, so I mean, it might be true, but so the way we did it is, of course, you use some Pauli-Lashego inequality for Steiner symmetrization. And then there's a case of equality in this inequality, which sort of gives a condition on the measure where directional derivatives vanishes.
Mm-hmm.
And in the plane, we strongly use that, well, maybe you can do this in high dimension, but our thought was that we use that if the measure of this set is positive, and in the plane, p-harmonic functions are real analytic outside the critical points. So then this cannot happen. But I don't know how to draw that conclusion in higher dimensions.
Mm-hmm. Okay. For the Schwarz symmetrization, as I remember, it is the paper of Zimmer and brothers. This result. That the case of equality,
right.
yes, and this is quite recent result for the Steiner symmetrization.
Right. Yeah.
Mm-hmm. Yeah, it's very interesting. Mm-hmm. Yeah. Okay.
But yeah, I mean, I would be happy to see if you can sort of exclude this also in higher dimensions. But yeah, I don't know.
Okay. In many problems, 3 is equal to infinity in the sense of dimensions. Yeah. Okay. Then maybe you can show the beginning of your talk when you discussed the historical remarks.
Sure. Yeah. Probably you know Marx pretty well. Let's see, where were we? No, here. I think. Is this what you
yes, maybe a bit earlier. The paper by you looked, you showed the case P equal to.
Oh yeah, okay. In this this argument, you mean?
Yes, and it is. It is by Kavol in what year?
So I think so. The original proof of this is from 1990 by Peter Lindgren, and then there is a paper by Beloni and Kavol from 2002 where they sort of attempt this proof.
This argument, yes. And by the way, it works for arbitrary Q less or equal than P.
Yeah, right. So there's also
Yes,
some
and it is in some of my papers, but I believe that it was used earlier. And Kavol himself attributed to this trick to Rafael Ben-Gurion.
Okay.
To the, as I remember, to the thesis of Rafael Ben-Gurion, but I don't remember in which paper of Kavol was it written. Yeah, but yes.
Right. Okay, thank you.
Well, then you say that for P less than for Q less than P, it was proved in 95. Yes, a bit later. Yes,
I said that. Yeah, I think that's the. Yeah.
Maybe.
Yes.
Maybe.
But yeah, I think for Q less than P, there, this is mentioned in many papers, but.
Yes. Okay. Maybe I did not know about this paper. Yeah, I discovered it from the sale. But yes, and then a bit later also some maybe strange strange result. Okay. This is about non-uniqueness. Please.
Okay, you mean these two in the
yes, the last one.
Yeah.
The last one. It is quite strange because the fact that for Q greater than P, you have non-uniqueness in how to say, гантелеобразная.
Simply connected?
Dumbbell domain.
A dumbbell.
Dumbbell domain. It is quite earlier. I knew it in the beginning, in 2000. So it was written much earlier.
Okay.
So, and I think also for arbitrary P, so it is quite strange that somebody wrote it in 2019.
Okay. So do you know which do you know where to find that?
Yeah, it should be. Yeah.
No, because I asked them, and they I think the main reason that they wrote it down was that because they couldn't find an example of
it. Eric, nobody can find anything. Yeah, it is well known. The classical 1D result, which is in this inequality. By the way, the Poincaré inequality is for zero mean value. For this, for zero at the boundary, the first result was by Steklov.
Okay, I see.
And moreover, in fact, I can recommend you our survey in the journal Mathematica. 2015. It is also in Arxiv, if you wish. Kuznetsov and Nazarov. Sasha знает.
I think I've seen it actually.
We wrote about sharp constants. I'm almost sure that we did not find all what was known at that moment, but many results, and in particular, more or less all the classical results of the 1890s and 1900. These years when this story began.
Okay.
Yeah. Well. Okay. Beg the pardon. Other questions or comments?
I have one question. So, and here on the slide of uniqueness, P could be equal to infinity too?
So in fact, yeah, when you send P to infinity, the problem changes dramatically. So it turns out that when P goes to infinity, well, depending on if, let's say, P and Q goes to infinity, then you lose a lot of the uniqueness of minimizers of the quotient. And what people have been doing more is studying the limiting equation and looking for solutions of that. So there's a whole, as a whole story by itself, I would say. But these are quite interesting, and there are some counterexamples of uniqueness, and there are some results regarding uniqueness too, but not basically in the case for minimizers, more for solutions of an equation.
For in 1D case, there is uniqueness.
Yeah.
But for some complicated domains, for example, in the annulus, you will not have uniqueness, just because you anyway should have. Okay.
So basically for P and Q is infinity. For the quotient, the distance function in the set is always a minimizer. So, and then if you can take the largest ball inscribed in omega, if that does not coincide with omega itself, then you always have several minimizers. So yeah, this is a little bit different when you send P to infinity.
Yes.
Okay, and one more question. So you said in the end, the open problems for higher eigenvalues. So it is not known, there is no results, or there are some results, but
I think people haven't really defined. Okay, I'm not 100% sure, but I think I haven't read at least that people define eigenvalues.
Excuse me, but what do you mean when you say about eigenvalues?
I mean the uniqueness of.
Not you. But when Eric says about the second, for example, eigenvalue, what do you mean?
You could think of other critical points maybe of this.
For example, with two opposite direction deltas.
No, so okay, maybe that happens. I don't know. I mean, but what? Yeah, I mean, one way of defining it could be maybe looking at the energy, which is the gradient, LP norm of the gradient, and then you look at critical points on the L infinity sphere. I don't know if this makes. I haven't studied it, but maybe you can do something interesting about it.
Okay, maybe. I don't like infinity. It is very far. It is quite difficult to work with what is near me.
No, I agree. But actually, what you mentioned there with two deltas. So if you look at the true inequality with the Helder norm, it's a semi-norm. In fact, this is exactly what happens. You get one delta plus and one delta minus.
Yes, I see. Yeah. I should think. I have some results in this area, but they are just about 2004. Maybe I can.
Yeah.
Send
Please
it
share with
to
me.
you. And anyway, just in this February, we wrote a small one-dimensional survey.
Okay.
Yeah, you can find it also in Arxiv.
Okay. Thanks.
Okay, more questions?
I have a simple question, just clarifying one. So it's about Euler-Lagrange equation. So am I right that you assumed there that the domain omega has to be connected when we pass from the critical point to the Euler-Lagrange equation?
Let's say
with L infinity.
Okay, let me think here.
Domain is connected by definition.
Yeah,
Yes.
sorry, connected open set, I would say.
Because if it's not connected, I guess you can have two copies of the domain, and then you might have a solution there or not. So it cannot.
In fact, the dumbbell can be considered as a small perturbation of two balls, disjoint balls. It is just the case.
Yeah, I just asked because in these papers by Brasca and Francina, they showed that there are some peculiarities caused by, say, not connectedness if L infinity norm is substituted by LQ norm. So that's why I just asked.
But
I thought maybe something similar happens here as well. So
I mean, I know it's a good question, and I haven't really thought in that direction, but that's a good point. Thanks.
Okay. Володя, может быть, мы потом это обсудим, кстати. Well, okay, thank you once more. Так, Даш, заканчиваем.